Hi everyone. So today we are going to discuss one very important theorem of series of functions. Okay. So you know that when we discuss any theorem of series of function, first always we consider a sequence of partial sum, right? So here also I will consider a sequence of partial sum. Okay. So what will I do? Let Sn be a sequence of partial sum of series summation Fn. What is meaning of it? Sn of x is equal to, tell me, Sn of x is equal to what? Yeah, right. F1 of x plus F2 of x plus and so on Fn of x. Okay, so whatever the theorem of series, always this is our first sentence. Okay, so let us go further. So let us think about what is the given information here. So here summation Fn is a series of R integrable function. Okay, that thing I am going to write. We have summation Fn is a series of R integrable functions on closed interval AB. That means each Fn is R integrable. Getting it's a series of R integrable functions. That means each Fn is R integrable on closed interval AB. Okay, see, each Fn is R integrable. That means, see what we do here. We take a finite sum of integrable functions, so that's why Sn of x is also R integrable. Since we are adding integrable functions, no, so their sum is also R integrable. Therefore Sn is equal to f1 plus f2 plus and so on Fn is R integrable on closed interval AB. See, I'm going to call it as equation number star, since I'm going to use it later. Okay. See, let us move towards the second information. What is the second information? That summation Fn converging uniformly to F. Okay, so I will write, we have summation Fn converges uniformly to F on closed interval AB. See, as summation Fn converges, corresponding sequence of partial sum also converges. Therefore, sequence Sn also converges uniformly to F on closed interval AB. Okay, so I will call it as equation double star. Sorry, it's not equation, it's statement. Okay, so now let us combine star and double star. Tell me what will I get? See, I will write from star and double star what we have got. What we have got? Sn is R integrable from star. Sn is R integrable on closed interval AB and it converges uniformly to F on closed interval AB. See, but this theorem already we have seen in a sequence of function. Sn is R integrable and converges uniformly to F. Then F is also R integrable. We have already proved. So therefore, F is R integrable on closed interval AB. See, here I am writing, proof is required. So that means you're supposed to write its proof. Getting now, already we have proved this part. And one more thing we had that time. You remember what we had? Yeah, yeah, you remember? Try to say f is R integrable, and one more thing we had written that time. Yeah, try to recall it. Yeah, you're right. Yeah, what is it? Integration a to b, limit n tends to infinity s1 of x is equal to limit n tends to infinity integration a to b s1 of x. That means what does it say? It says you can interchange limit and integration. Okay, so here integration was outside, limit was inside. Here we wrote integration inside and limit outside. Okay, so now let us put the value of Sn of x. What is Sn of x? Already we have written at the top. Sn of x means f1 plus f2 plus and so on fn. Na? So here at both sides I will write the value of Sn of x. Okay, so we put the value of Sn of x, f1 plus and so on fn on both sides. Okay, so see, can I write this thing in a form of summation? Yeah, obviously this is nothing but summation fk, k running from 1 to n. Okay, so I wrote, this is nothing but, see, I will show you what you have written. So here f1 f2 plus and so on fn, now we had added, no, so simply I replace it by summation. So let us think about the right hand side. So in right hand side, if addition is there and integration, if addition is there, we take separate integration. So here also I can take separate integration. So therefore we get, okay, so this one we get. Okay, so after that what shall we do? See, here we are taking n tends to infinity now. So here summation simply from 1 to infinity fn of x, right? Okay, so I write summation k running from 1 to infinity. Okay, so if you think about right hand side, so we are adding something, so we can write in a form of summation. So therefore, limit n tends to infinity, summation k running from 1 to n, integration a to b fk of x dx. Okay, so I wrote in a form of summation. That sum I replace it by summation. Okay, so see, when you have summation fk k running from 1 to infinity, but we know that that summation fk converges uniformly to f. So that's why when you take a summation k running from 1 to infinity, its value is nothing but f of x. So therefore, this is simply f of x dx, since value of that summation is f of x. Okay, so let us think about right hand side. In the right hand side, we take k running from 1 to n. Na? So here we are taking n tends to infinity. So simply we can write k running from 1 to infinity. Okay, so we get this one. Okay, so here either you write k or n, both of them are variables, so it doesn't matter. So instead of k, I can write n also. Okay, and hence we get the required statement. Since we had to prove the same thing, we had to prove the same thing, and we have proved it now. Okay, thank you.